Alright, this lesson is on logarithmic functions. We're going to tie in a little bit of the work we did with exponential functions into how a log function is related. The best thing probably to show at this point is a short little video that talks about log functions. The video is a few minutes long, but I think if you take some notes, make sure that you are able to copy down the numbers that appear on your screen. It'll really help, and it'll explain logs, and it's kind of full of sense. So let's take a look at the video, and again, make sure you have a piece of paper and a pencil to record these numbers. So here we go. So there'll be some numbers appearing on your screen here in a minute. Talking about theoretical pull, 11,240 pounds. And then, of course, you want to record this is 10,000 pounds of feed force. That's pretty impressive and really important when we're dealing with logs. So as long as you're getting this all down, I believe, yeah, this is the part 16 feet per second, FPS, feet per second, dealing with logs. And okay, we'll stop it there because that video actually has nothing to do with logs at all. It's really just a video about this logging company. So, having said that, let's move on. All right, now we're looking at something much more familiar to us, and that's math. So, looking at the math involved here, we've looked at the function y equals b to the power x, the exponential function, where b clearly in this case is greater than 1. And we've also looked at the inverse equation, which is a reflection over the line y equals x. And so this blue line indicates to us the inverse equation. And the previous days you've looked at how to rewrite the equation in inverse form. And what you said is you need to switch your x and y's. Then you can rearrange the equation. What we want to do is many times we are solving for the y value, and sometimes the y value is tucked up here in the exponent. This makes it a little bit difficult for us to solve, and we'll take a look at some questions from grade 11, such as 27 is equal to 3 to the power x. And in grade 11 you were asked to solve this. What value would you substitute in for x that would equal 27? And so you quickly establish by trial and error that 3 to the power 3 is in fact 27. So therefore x would be equal to 3. And you could continue to do that. You solved for the exponent, much like we're doing here. The difficulty is when you began to solve for questions that didn't work out to nice numbers. And by that I mean, instead of 27, what if it was 26 is equal to 3 to the power x? Now in this case, there is no value, no whole number that we can plug in for x. But what we would have done in grade 11 is we would have tried some trial and error. And so I might have tried 3 to the power 2 decimal 9. And 3 to the power 2 decimal 9 works out to a number really close to 27. And that's about approximately 24. So maybe 2.95, and I would kind of trial and error it and get to about the approximate number. And that method was fine for grade 11, but in grade 12 we have a much better way of solving for this. And what we see is the same graph with the same initial equation, but what we start to see is the equation written not in inverse form, but in what we call logarithmic form. And so these two graphs are clearly the same. These two equations then must be similar as well. And so what we're going to look at is we're going to look at the relationship of x is equal b to the power y, and the fact that you can rewrite it in the form of y equals log base b x. And the reason we might do this is because sometimes we want to find that value of y or find that exponent, and we're used to writing y equals something. And this is where logs can help us out. So, by definition, any exponential relationship can be written using the logarithmic notation. So if you take a known equation, like 2 to the power 3 is equal to 8, you can write it as follows. We always start with the exponent. So 3 equals, it is going to be the log form, and you'll notice the base here is 2, so we keep the base 2. And then we write the number that we haven't written yet, which is 8. And we'll show you later on how that's equal using the calculator. So another question, another practice one we could look at is 2, starting with exponent 2 is equal to log the base 5, 25, and these are equivalent. And so the general rule is right here. Always look at solving for s equals log of the same base r and then t. The true definition is right here. The logarithmic function is defined by y equals log base bx, or y equals logarithm of x to the base b. There's a number of different ways you can say this, but that b is clearly in kind of the subscript area. There are restrictions, much like there was with exponentials. B needs to be greater than 0 and b not equal to 1. So let's go ahead and talk just very briefly about where logs came from, because logs today are calculated on a calculator, and that's making things much, much easier than we used to have. Years ago, every textbook would have log tables in the back, and students would have to be able to line up the values as well as the decimals and come up with a digit here, and then they need to add it to a digit over here. There's quite a little process. It wasn't difficult, but there was a lot of tables, and you're also limited to the numbers that you could solve. Another method, an improved method, was something called the slide rule. And ask your parents or maybe even your grandparents about a slide rule. These were amazing tools. We've got a couple in class that you can take a look at. But they did all sorts of math, and every high school student would have had a slide rule during that time. Luckily for you people, you can jump right into looking at solving logs using a calculator, which is really just a very big log table. Here are some applications or ways that logarithms come in handy. To find a number of payments on a loan or the time to reach an investment goal, log calculations will work. To model any natural processes, looking at loudness, sound intensity. There's a number of things like pH or Richter scale that are based upon a log scale, and we need logs to calculate some incredibly large or small numbers. There's just a little bit more information here. This really isn't going to come into play in what we're looking at, but you could read that through. So very quickly, if we are taking a exponential function and writing it as its inverse, we notice that we just switch the x and y's around to get their original. The log form of the inverse, it looks something like this. Start with the exponent, y equals, followed by the word log. The base is b up here, so the base is b down here, followed by x. These two equations are the same. They represent the same graph, the same function. These two are the inverse of this exponential function. So if you have a situation where you're looking at an equation and you need to solve for the exponent, you can write its log form and solve for the exponent, and we'll see a number of cases with that. So just for practice, we want to rewrite some log form. So if you want to pause and try these on your own, I will show you the video once we're finished. So here are the three equations. I don't know if you can see the one at the bottom, but there are the three written in log form. Now I'm going to get you to pause it once again, and what I'm going to do is I'm going to show a little relationship of why the right hand side is equal to 4. Okay, looking at the first one in blue, what I've done is I've wrote 16 as the same base as what I had over here, the same base. And when I do that, 16 can be represented as 2 to the power 4. Now you'll notice that the 2's are the same, and the solution to the whole right hand side is equal to 4. Now we can show this on a calculator later on, but that is in fact true. If we look at what I've done on the right hand side here, I've changed 1 over 9 to 1 over 3 squared, which is still 1 over 9. Then I've written it as a negative reciprocal, and I've noticed once these two numbers are the same, whatever the exponent is the solution. And this is something that we are going to see a number of times. Please read the note down here about negative bases and what happens when you have the base is 0. The next slide involves evaluating or solving for the equation. And we can take that same approach as we had before. One approach is to take a look at 81 and can you write it with a similar base as there. So can you write 81 as 3 to the power something? And if you think about it for a minute, you see that 3 to the power 4 is equal to 81. Well, when these two numbers are the same, the answer is just simply 4. Another way of solving for this is writing it as a log and then rewriting it as an exponent. So this exponent looks like this: 3 to the power y, so the base 3 to the power y is equal to 81. And now think grade 11, what is the value of y that would make this left hand side 81? And you would see that it would be 4. Therefore y is equal to 4. Same answer, a different approach. Grade 11 approach, grade 12 approach. Let's try this one. So I'm going to pause it, take an opportunity to try both of these, and then we'll take a look at the solution. Okay, looking at the solution, once again, the left hand side is grade 12, right hand side is grade 11. Grade 12 approach down here, I recognize that decimal 01 is the same thing as 1 over 100, which is the same thing as 10 to the negative 2. So what we've noticed, and a little rule down here, something that you're going to want to remember, is that when you have the base and the next number beside it the same, the answer is always going to be whatever the exponent is. This is a very important point, talking about something called common logarithms. When writing a common log, it's not necessary to write the base. So for example, if I were to write the log of 7, that actually is really the log base 10, 7. Now common logs are important because on our calculator we have a log button. That log button only calculates common logs. And what I mean by that is if I had a log base 3, 7, I can't do it right away on the calculator. I don't know what it is. There is a way to do it, and in future lessons we'll be able to do that. Or you could do a quick Google search and figure out how to solve something like this. This exercise, rewrite in exponential form. So exponential means get it out of log form. So we start with the base in this particular case. 4 to the power 3 is equal to 64. Remember that there's nothing there, but really it is a base 10, so 10 to the power y is equal to x. Example 4, find an approximate value for each log. So approximate value means get as close as you can. So what I'm going to do is I'm going to write this out as y equals log base 2 10, and I'm going to rewrite it as its exponential. So let's write it as 2 to the y is equal to 10. Now, because there is no number that works out exactly to 10, I'm going to have to approximate. So this is what I'm going to look at. I'm going to say, well, I know that 2 to the power 3 is 8, and I know that 2 to the power 4 is 16. Now 10 is closer to 8, so my answer should be closer to 3 than it should be to 4. So I might do an estimate and say I think the answer is about 3 decimal, let's say 3 decimal 2. And then I could work through my calculator and solve that. This isn't a very efficient way, but as an approximate value, this is what I'm looking at. Same thing holds true here. I'm going to make this equal to x. The base is 10, even though it's not written in, we understand it is. And so 10 to the power x is equal to 2500. Again, there's no value that I can plug in right now I can see that will equal 2500, so I'm going to use some estimations. So I'm going to use 10 to the power 3, which is 1000, and 10 to the power 4, which is 10,000. And I'm going to use the same approach. I know that 2500 is closer to 1000, so I'm going to think that it's a smaller number, and I'm going to estimate that it's maybe 3.3. And this isn't great, but again, as a rule, a self-check, when you actually do figure out how to solve this question, that's really what we're after. So you can go ahead and try and figure out how to do that, and that's a great little skill. Here are key concepts. Again, pay particular attention down to the exponentials and the certain rules and restrictions. If you ever get confused, think about what happens with restrictions with exponential functions. Here's your assignment. Again, try and focus on the last sort of 4 groups of questions here. And finally, just leaving you with a little joke here. Do zombies eat popcorn with their fingers? And of course you're looking at this and your answer, no, they eat the fingers separately.